Okay, welcome back to the Wireless Channel, everybody. Today we will have a presentation delivered by Michele Mirabella from the University of Modena in Reggio Emilia. I'm very happy to have the collaboration with them. Michele is here, Pasquale is here, my dear friend Professor Giorgio Vitetta is also here, as well as some of my team members. Yeah, let's enjoy the talk. Please, Michele, take it away.
Thank you for your kind presentation. Hello, everyone, and welcome. Today, we are diving into the future of 6G waveforms because while most of the world is getting used to 5G, the research community is already looking for ways to handle extreme mobility. Think, for example, of high-speed trains or even supersonic UAVs. My name is Michele Mirabella. I am a postdoc researcher from the University of Modena and Reggio Emilia, and today I'll present our joint work that is called Continuous Time Analysis of AFDM, Pulse Shaping, Fundamental Bounds, and Impact of Hardware Impairment. To guide us through this, we'll start with the why. So the motivation behind the use of affine frequency division multiplexing. Then we'll move to build the first rigorous continuous time framework for this kind of waveform. We look at how it actually sounds and looks in the spectrum using the power spectral density, how it handles hardware impairments, and finally we'll establish the fundamental limits of how well it can sense the environment if used as a radar waveform. So why do we need this? 6G isn't just about faster video downloads. It is about extreme mobility, as I said. And when a receiver moves fast, the signal experiences doubly selective fading, which is a mixture of time shift from multipath and frequency shift caused by the Doppler effect. Our current standard, used also in Wi-Fi, Bluetooth, and other well-established technologies, is AFDM. But AFDM struggles in this case with doubly selective fading because this kind of shift destroyed the orthogonality among subcarriers. On the other hand, OTFS, or orthogonal time frequency space, that is a more recent modulation, it's a great alternative, but it comes at the price of a very high computational price tag for data detection. And that brings us to the new contender. Here it comes AFDM. AFDM is a very recent and flexible waveform that uses a tunable chirp index named lambda 1. Actually, there are a pair of chirp indexes, lambda 1 and lambda 2, but today we are just focusing on the one that is more related to physical and continuous time aspects, that is lambda 1. By adjusting this index, we can separate the multipath component and achieve full diversity. Nevertheless, this modulation has proven to be very attractive also for integrated sensing and communication, or ISAC, because it enables also estimating delay and Doppler simultaneously while transmitting information. However, there's a catch, because almost all existing literature about AFDM focuses on discrete time models. But hardware, doesn't work in discrete jumps in practice. It works in continuous time. So if we ignore that, we miss some important physical aspect. And what exactly do we miss? The discrete time models miss the analog aspects, such as pulse shaping, fractional delays, and also fractional Doppler, I would add, out-of-band emissions, some limits for the local oscillator impairments, and the fundamental bounds for sensing. Our contribution tries to fill this gap, since we provide for the first time the continuous time framework for AFDM, leveraging the affine Fourier series. We analyze the power spectral density of AFDM, quantify the impact of some hardware impairments. Among these, we recall the phase noise, carrier frequency offset, and the sampling jitter. And we also provide closed form expression for the Kramer-Rao bound for the problem of estimating delay and Doppler using AFDM. We are not starting from scratch, because detailed continuous time models already exist in the literature for OFDM, for OTFS, and other more complicated variants of them. Yet there's still a gap for AFDM. And through this work, we want to bring AFDM to a higher maturity level. Let us look now under the hood. The basic generating principle of AFDM is the inverse discrete affine Fourier transform. Unlike OFDM, where the phase of the signal evolves linearly, AFDM uses a quadratic phase evolution, resembling more like a chirp radar waveform. But the key concept here is, after this mapping, what you need to add is the so-called chirp periodic prefix that extends the discrete time samples of the signal. And you can see here in the plots the main difference between OFDM. So the chirp periodicity extension makes your samples repeat over the period in a way fundamentally different from OFDM, and this is the first ingredient of AFDM generation. If you analyze the continuous time signal, so basically these discrete time samples feed a pulse amplitude modulator, and so in this way the continuous time model is generated. And the continuous time signal can be analyzed through the so-called affine Fourier series. That is a generalization of the Fourier series that is suited for chirp periodic signals. So signals that repeat, but a phase term difference, a quadratic phase term difference over the periods. And the resulting model shows that each subcarrier coefficient, Sm, is weighted by the pulse P in a way that if you select your pulse shaping filter poorly, you end up distorting your data even before they leave the antenna. So it is very important, this result, because it tells you pulse shaping is a fundamental task. And now, if we consider the signal and want it to be band limited, the very first thing you have to do is selecting the proper pulse shape. In our work, we propose using the root raised cosine pulse, also called RRC. And since this pulse has some roll-off regions, of course, we must suppress some subcarriers at the edges to avoid spectral overlapping. And the subcarrier suppression mechanism isn't just something that deals with the common hardware problem. It is a trick that enables you to make your signal a multi-carrier signal without self-interference. So in this way, you don't complicate the receiver architecture too much. Let us now visualize the difference between the continuous time models. On the left plot, you see the magnitude evolution over time. On the right plot, you see the phase evolution over time. And this is what it is of more interest for us, because the AFDM phase is quadratic, whereas the OFDM one is piecewise constant. And this quadratic phase evolution is what enables the receiver to better separate the multipath components after the signal experiences double selectivity. So regarding the channel, when the signal is sent through the channel model can be regarded as the one shown in the first equation. It is a channel impulse response with L paths and some delays and Doppler, and also complex magnitudes. In our model, we derived basically the input-output relationship, so the relationship that tells you if you transmit something, this is what you receive. And the matrix H is also called effective channel matrix, for which we have the expression of its M-end component that contains also the effect of pulse shaping. And most importantly, it is the interaction between the paths is governed by the so-called Dirichlet kernel, that is the function G, that basically tells you how much intercarrier interference we are going to suffer based on the mobility of the environment. Now, how much space does AFDM take up in the air? To understand this, we derive the power spectral density. This is something made possible by the continuous time model. And one interesting finding is that this expression is not so different from the OFDM1, But the most important thing is that it contains a fundamental difference that is expressed by the convolution inside the square absolute value. This convolution between the pulse and the function W tells you that if I use a chirp index lambda1 different from 0, so if I'm using AFDM and not OFDM, what we are increasing are the side lobes of the spectrum, because every convolution enlarges the spectrum. In other words, AFDM can be leakier than OFDM if you don't manage your pulse shaping carefully. We can also visualize this. Here we have two plots, one on the right and one on the left. Let's start with the one on the left that shows you the PSD comparison between OFDM, AFDM, and a variant of OTFS that is called OTFS with double cyclic prefix. All the three modulation occupy the same bandwidth they are basically generated using an infinite duration ideal band limited pulses. On the right plots instead, you see the use of truncated pulses. That is something that in real hardware is always the case. And here a significant difference is that the AFDM out-of-band emissions are 7 dB higher than the OFDM ones. And this is really important. Moving on in the analysis, you know that real hardware is never perfect. We analyze three main hardware impairments, namely the phase noise, the carrier frequency offset, and the sampling jitter. Without going into the little details of the math, the main result is that all these impairment actually smear the delay and Doppler components inside the Dirichlet kernel. So an important remark here is that since AFDM is naturally more resilient to intercarrier interference expressed by the Dirichlet kernel, it is also more resilient to these hardware impairments than OFDM. Moving to the sensing side of things, we calculated, as I said, the Kramer-Rao bounds, basically the limit for how accurately we can estimate the distance and speed if we want to use AFDM as a radar waveform. The interesting trade-off here is that using a chirp index lambda1 different from 0 actually raises the estimation bound slightly compared to the OFDM case, so when you put lambda1 equal to 0. And this is, of course, a trade-off, but is a price worth paying because, as you know, AFDM allows us to resolve the Doppler ambiguities that would leave otherwise OFDM completely without solution in the presence of joint multipath and Doppler effects. Regarding the pulse shaping, we compare different options. The first is the root raised cosine that is shown in the plot with the red curve, and other two pulses that are the Gaussian pulse in blue and the rectangular pulse in green. Of course, here we are seeing their spectrum because it is something that interests us, also in light of the subcarrier suppression mechanism. Of course, as you can see, the root raised cosine pulse has the nice property of having a flat top spectrum, and this is important because it means it treats all the subcarriers, all the active subcarriers equally. On the other hand, the rectangular and the Gaussian pulses show amplitude fluctuation, meaning that they distort the amplitude of the subcarriers. And this makes the receiver jobs much harder. And for such pulses, we need to set up a tolerance to limit the fluctuation in the passband. Regarding the subcarrier suppression mechanism, if you, for example, focus on a single subcarrier, let's focus on the purple diamonds on the left and move either on the left or on the right by n samples, so by a period. Either we must find a pulse null or we shall suppress the carrier by setting the current symbol to 0. This is necessary, of course, not just to avoid self-interference, but to obtain, as I mentioned before, a multi-carrier signal. When we look at the sensing accuracy, using the Kramer-Rao bound, these are Kramer-Rao bound plots, the root raised cosine turns out to be the best again, and since it achieves the lowest bound for both delay and Doppler estimation. Of course, the green curve cannot be easily seen because it overlaps with the red curve that corresponds to OFDM case, but of course they achieve the lowest values. Let me then move to communication performance side of things. If we look at for example, at the bit error rate, the discrete time models that are represented by the dashed lines in these figures is too optimistic because it underestimates the error. On the other hand, the continuous time models, so the solid lines, show a higher and more realistic error rate. These are, for example, two different channel realization. The first consider different maximum path velocity with a fixed number of channel paths, and the other one does the opposite operation. So it fixes the maximum path velocity and varies the number of paths. Finally, let's look at the hardware resilience of AFDM. In every category, phase noise, carrier frequency offset, and sampling jitter, the AFDM, so the continuous line, outperforms OFDM, the dashed lines. And the main take-home message here is that AFDM is naturally more resilient to intercarrier interference caused by double selectivity. So while OFDM hits a very high error floor where it just stops improving, AFDM keeps getting better as the signal-to-noise ratio increases. To wrap up and conclude, we have built the very first rigorous continuous time model for AFDM. We have shown that through the power spectral density that while AFDM has some spectral challenges with out-of-band emissions, it is more resilient to doubly selective fading and the hardware impairments we have considered. Nevertheless, we have also derived for the first time the sensing limits using AFDM when we consider the continuous time model and also including the pulse shaping effect in the Kramer-Rao bound. Future tasks will be looking into new receiver architecture and pilot designs that can take full advantage of this continuous time model. So from my side, I've done. These are the references cited in this presentation. And so thank you for your attention. In case you have any question, don't hesitate to ask.
Yes, thank you very much, Michele. Guys, any questions?
Maybe I can ask one first.
Go ahead.
So
Okay.
first of all, thank you very much for the nice presentation. It's really nice to see all of these figures and understand better of the work. And one just a motivational question is, regarding now that we've analyzed AFDM over more realistic scenarios, not these ideal discrete case. Now we consider the continuous analysis, the pulses, and the hardware impairments. How do you see in terms of implementing this AFDM real life, like for deployment, which of these do you think would be the most significant?
Well, in my opinion, one of the most significant problem will be phase noise, because you want to keep your phase as much as possible quadratic phase. So phase noise is going to affect also the sensing performance in particular. So but in general, all these impairment will have a greater impact if you want to deploy AFDM in Isaac. But of course, it is more resilient to OFDM.
I see. Okay. Thank you very much.
Anybody else? Thank you, Eric. Anybody else? Any other comments, questions? Go
I
ahead.
have a quick question actually. So I think it was very nice presentation. Thank you. So I actually understood quite a lot. I just have a question regarding the start of the receiver chain. Do you consider synchronization at all here? And if you do or if you do not, what do you think will be the consequences of using this model in terms of synchronization for AFDM?
Of course, in this model, I am assuming perfect synchronization at the receiver because this is just the very first steps into the this formulation of continuous time modeling. Of course, synchronization can be done using the conventional techniques of AFDM. This is my very first comment, but of course we need to explore it in deep details.
I see. And do you think your continuous time model would help in that case to model the synchronization better?
Well, of course, yes, because it is more in contact with the hardware reality. So the synchronization aspect are going to somehow been partly included in the non-idealities we considered. So in this case, phase noise, carrier frequency offset, and sampling jitter. Probably, if you consider, for example, time synchronization, it can be regarded as a form of sampling jitter, or at least its analysis that is more related to timing offset can be done using the same math deployed for the analysis of the sampling jitter. If you instead consider carrier frequency offset synchronization, any residual frequency offset will be regarded as carrier frequency offset, and so it can be added to the model in this way.
Okay, got it. And I think one final thing is how easy would it be to extend this model to MIMO? Because as far as I can see, this is still a SISO system, right?
Sure. You basically can employ this model and using the convention. So you just use the model we obtained here, the input-output relationship we have obtained here, and the extension to MIMO will be done by using the conventional MIMO channel. So every pair of transmit and receive antennas will see its own channel, supposing that there is no extra interference between the different antennas. And then the extension will be done directly using this discrete time formulation that in this case starts from a continuous time analysis.
I see. Okay, that makes sense. Okay, thank you.
You're welcome.
Thank you, Ryan. Thank you also, Michele, for the wonderful talk. If there is no any further questions, I think also in the interest of time, we can call it a day. And I thank you again all for being here. And I see you next time in the wireless channel.